right. So I believe I am ready again. Yet again. We go again. So hello world. We're gonna go ahead and give again. So, let Twitter know that we're out there. Okay, majority element number 2. Let's go. We've done one problem tonight. Let's see if we get another one done before the end of the night. See how that goes. Given an integer array of size n, find all elements that appear more than the floor of n over 3 times. Oh. Could you solve this problem in linear time and constant space? Now this is an interesting question. So this is okay. This is a very interesting question. Basically, you can count. It's kind of funky, but what you could do, I believe, more than the floor of n over 3. So it's got to be at least the floor of n over 3 plus 1. So doing this in linear time and in constant space is a very interesting question. Apparently you can do some funky bit manipulation stuff with integers and pretty much count the number of bits that you see. I don't recall exactly how it works. It's something like, yeah, you can count the number of, how does it work? Count the number of times you see a certain bit, and take that modulo. Oh, I'm not sure now. Actually, I actually I think I'm confusing this with a different question. So I mean, obviously, one way to do this is to use a hash map, and you do a frequency map. Really, is what it's called, and you count. You basically figure out how many times a particular element, for every element, how many times that element appears, and then you can just run through the frequencies at the end to figure out which elements you should put in your result. However, that's linear time, but not constant space. To do it in constant space, you're going to want to do some bit manipulation shenanigans, which is fun. However, I want to say something like, all of the bits that appear at least the floor of n over 3 plus 1 times, all of those bits, you want to keep those bits. The bits that don't appear that many times, you don't want to keep them, I guess. Something like that. How do we do this? Oh, this is definitely an interesting question. Yeah, think about this. This is gonna take more than 20 minutes. Probably take more than 20 minutes. Excuse me. I forgot the the question that's related to this that I forgot. But yeah, it's you want to basically you have a bit vector, and you can store that in a single integer, or rather no, it's a bit vector, but it's constant. It's constant. There's a constant number of bits, so it's constant space. Right, there's only 32 bits that we're working with here. So, you can count how many times you see a particular bit, how many times you see it as a 1, and I want to say something like if you were to take all the bits that you see at least floor of n over 3 plus 1 times, because it's floor of n over 3 plus 1, if you take those bits modulo 3, there should always be a 1. Well, if you take all of the you take all of those bits modulo 3, if they appear, if a number appears, well, if you take it modulo this value, whatever this value is, take it modulo this value, all those bits should be zeros. The problem with taking modulo that value is, or yeah, problem with taking modulo that value is it's more than that many times, right? So it's got to be not. That's kind of hard to gauge. It's not exactly some it's not exactly divisible by 3. It's actually greater than that. If you divide by this, right, modulo would be taking the remainder, right? If you divide by this and the integer part is more than 1, that's encouraging. Is it possible that the bits, well, it would have to be all the bits. Well, is it possible that you could, no, it's not. So okay, it's a pretty interesting question, because if you had another number that was floor over n over 3 plus 1 times it appeared, if you add, so you could have at most 2 numbers, really. That's what I'm trying to get at, is that you could have at most 2 numbers that show up in the output. You could prove that, because if you have a third number, obviously this is going to be over, if n is divisible by 3, then this is just n over 3 plus 1 times quantity times 2, which is, if you added another n over 3 plus 1, you'd be n plus 3, which is too many elements, right? You don't have enough elements to have 3 elements. So you only have, there's 2 numbers possible at most. You have at most 2 numbers. You could even have 0, 1, or 2 numbers that appear. Yes, you can't have 3 numbers that appear in the result. So that's pretty interesting. The tricky thing would be then, okay, you need to find, do any of these bits appear more than this number of times? If they do, collect them, and if any of them appear twice this number of times, more than twice, so if any of them appear between 1 and 2 times, that must belong to the first number. those must belong to the first number. Everything else has to be zeros. And if any of them appear, yeah, if any of them appear between if any of them appear rounded to 1, rounded down to 1, truncated to 1 times, if you divide by this number, whatever this value is, this floor of n over 3 plus 1, if you divide by that, and you have an integer of 1, that has to belong to one number. All of those have to be a 1. However, all of the cases where you have 2, where you divide by this value, and you have 2 as the integer, right? So there's at least twice. Those have to belong to both numbers. Now the question is, so those belong to both numbers. Those are shared between both numbers. However, you don't know which number you know what you can do? You don't know which bits belong to which number, though. That's the thing. You know what you can do? You can do 2 passes. 1 pass to find the first number where this is true, right? And then you could just remove all those bits from consideration. I used to you just subtract that many, all those from the bit vector. You just subtract all those numbers, and then all the values that you see. So yeah, you could do a check for 0 numbers by just passing through to see if wait a second, let me see. Oh no. Oh no. How do you? I don't know if you can do that. I'm sorry. No, never mind. I take that back. I don't think it's that easy. I was gonna say if you could do 1 pass to find out how many. No, you can't do that. 1 pass to find out how many. To find just if there are any numbers that appear more than that, more than a third of the time, a little more than over the third of the time. No, you need to. So the tricky part here is that if you have, let's say you have a bunch of 1s that do appear at least this number of times. They could actually be a disjoint set of numbers. So it could be 2 different numbers that appear a bunch of times in the array, and it could be a disjoint set of these, in which case you won't have any shared numbers where that appears, about. But this disjoint set, you don't know which ones belong to one number and which belongs to the other number. So it's hard to discern which one's which. You sort of have 2 different numbers now, where you have to figure out. What you could do is maybe, maybe you could, you now have like A plus B equals C, where C is the set of like if you had all of the bits, right? So if you added the 2 numbers together, that would give you that number C, which is the one you're looking at, where there's all these 1s. And you have this A plus B equals C. When you're considering the bits that are shared, you've got to what do you do? Those would be double counted for C, so you could just subtract 1 off, I think, if you added these 2 together. Yeah, so you just make that sort of idempotent, I guess. But then, yeah, then you got to figure out, okay, like there's, you could actually do a pass through to find out, at least one pass to find all for each pair A and B, what the other value is, the B for each A that sums up to C. I guess. I don't know if you can do it. Problem with that though is you wouldn't be linear space anymore. It wouldn't be constant space anymore. You'd have um, you don't have constant space anymore if you do that. Just thinking. Yeah, just counting the bits makes it kind of challenging because you don't know. You need to find one of the numbers, sort of. The thing is, it's like you could find another number, right, a number that has all those bits set, and then you could find the other number, and then you could check to see if both of those numbers are in the array, and then count how many there are of both of those. However, I think the problem with doing that is you could end up in a position where you're looking for, like, you might have to repeat that over and over again, something like that. Like, let's say there's another element in there, and like there could be a lot of different numbers in there that have sort of a pair where A and B are, when you add them together, give you C, something like that. And then for every one of those pairs, there's a lot. It could be a lot of those pairs. And for every one of those pairs, you have to do a linear search. That actually can give you a very expensive. That would be way too expensive. Potentially way too expensive. Challenging question, man. I'm fairly certain you got to count the number of bits that show up for each sort of position, each index. But what do you do with that information? That's an interesting question. That's an interesting question. I want to say if you do something with modulo 3, you might get something interesting. Because it appears, I don't think so though. I don't think it's all that useful. If you take modulo 3 of every bit. I want to say, yeah, dividing by 3 of every bit sounds kind of interesting. Seems interesting. If you only had one element that appeared more than that many times, but it is possible to have other numbers that have one of these bits that could appear this many times. It would be like a bunch of different numbers that share this one bit, and so when you count that bit, it shows up as one of these, and its count exceeds this n over 3 floor plus 1. Even though most of the numbers don't, or rather, yeah, there aren't that many numbers there that are the same. Excuse me. I mean, that's possible. Really interesting question. Interesting question. Just thinking, if you like looked at, yeah, I'm kind of stumped. If you looked at like, I don't know, what's the case that we could use? 2, 2, 5, 5, 1, right? So 5 over 3 floor would be, plus 1 would be 2. Right, so that's 1 2/3, 1, 2, yeah, so about 2. So 2 and so we would, now our algorithm would have to find 2 and 2 and 5 and 2 and 5, right? And 5 would be 4, 0, 1, and then 2 is 0, 1, 0, and obviously we have this 1 here. And our algorithm figures this out. Our algorithm figures this out. And yeah, so if we counted, I mean, if we counted the number of bits, we would get 3, 2, and 2. And we would conclude that every one of these bits is included, right? But it's not. Well, it is, but every one of them is, but it's split over I want to say something like we don't have to worry about this. Like the case I want to say is like if you had something like this. And somehow we had, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 over 3 plus 1 is 4. So we would need 4. Well, actually, in order for this number to show up, in order for one of these bits to show up, at least 4 times, it would either need to show up in the same number 4 times or 4 different numbers. But the thing is, if you have a number that shows up 4 times, then you don't have enough elements for another bit to show up that's not in either of the two. So if you have 2 numbers, then you won't have enough bits, you won't have enough numbers to get any other bits in there. If you only have 1 number though, excuse me, it is possible to get something else in there. However, and that would look like this, right? So you could have this situation where you really only have 1 number that shows up 1, 2, 3, 4 times, and everything else shows up a random number of times. And the issue here is I'm wondering if you take things modulo this value, take the number of bits modulo this value. I actually don't know, because you could have like the whole thing is just filled with the same number, and then you get all 0. Then you get all just 1 number all the way across, all the same bits. I'm not sure taking things modulo this value actually will do anything discernible, because you're just looking for at least that many. Take a modulo of that, then not really sure what you'll end up with, really. I guess if you take it, no, because you have other things that are just random number of bits. Like you're not going to be able to figure out which is which one, what to pay attention to, what not to pay attention to. I don't really know. This is a very interesting question. I have to ponder this for a while. It's kind of hard to discern if you have 2 numbers, then all of the numbers that exceed n over 3 floor plus 1 number that are greater than or equal to that number of numbers. If you know you have 2 different numbers, then all of those bits are relevant, right? They either belong to one number or the other. So that's good to know. If you have only 1 number though, then not all of those numbers will be relevant, right? Because we have these ones. This bit's not relevant. However, this one is. And how do we figure out which ones are relevant, which ones aren't? How do we figure out which bits are relevant, which ones aren't? I want to say something like you can count the number of numbers that have this bit, and then count the number of numbers that have this bit, which is really what you're doing when you count the bits, right? Count the number of numbers that have this bit, count the number of numbers that have this bit. I want to say something like when you remove excuse me. I want to say something like you could subtract away some of the bits. And they should all belong to a certain some combination of bits that you can subtract them away, and then what you've got left over. Like, yeah, this. I want to say that you could just like gather some, you can have some combination of these bits, some selection of these bits, and then check to see how many of that number shows up in the list. And there you go, that's your first number. However, I'm wondering if there's a way to discern between 0, 1, the 0, 1, and 2 case. If there's a way to figure that out. I want to say if you figure out the 0 case, then maybe you could figure out the 1 case, and then you could figure out the 2 case. Or go backwards if you could figure out it's not a 2 case, then it's a 1 case, it's not and then you can determine if it's not a 1 case, then it's a 0 case kind of a deal. Something like that. If you do something with modulo 3. I don't know though. Oh, that's kind of interesting. Yeah, if you break this up into 3 pieces, right? You split. So this is in the first. We said there's got to be at least 4 of these, right? So this is in the first piece, second piece, third piece. If you break it into 3 pieces, this will be in every piece with an extra 1 somewhere, right? This will sort of always be true if you take the floor of n over 3 plus 1. If this is n over 3, and this is n over 3, and this is n over 3, assuming n is divisible by 3, then you're always going to have 1 extra element in one of these pieces. But also, if you say it's at least, so there's always going to be at least 1 extra. Yeah, there's always going to be some amount. We don't know how many extra, but there's always going to be at least 1 extra. I mean, all that really means is that it's going to be greater than 1 when we divide by n over 3, I guess. Or yeah, dividing by this number. That's kind of what I wanted to do. So it's always like, yeah, greater than 1 or. The thing is, floor of n over 3, floor of n over 3, floor of n over 3. If n is like, well, n over 3 could only be, or n modulo 3 can only be a handful of things, right? It can only be 0, 1, or 2. Only so many extra elements left over. that's kind of interesting. You could do like, you could have one element left over 3 times. Just thinking, let's say you did like 14 divided by 3, right? That would give you 4, and then you'd have 2 extra elements left over. Excuse me, so if you broke this into groups of 4, you still have 2 left over. I don't know what I'm trying to do with that, or what I'm thinking with that. I don't know why. I'm just trying to figure out like some kind of a pattern or something recognizable. Well, definitely if you break this into n over 3 plus 1 pieces, then are you going to have 1 in each? Oh man. This doesn't really give us much to work with. I mean, I don't know what I'm trying to do exactly anyway. I want to say something like you could take this modulo 3, you know, and then you'll end up with, take all these bits modulo 3 and you'll end up with something at the end. Because, okay, maybe you do both. Maybe you do both. You say, all right, you've got to have at least this many bits for it to even matter, right? For that bit to even be considered. And then if you take this value, you take these numbers modulo, floor of n, just modulo 3, right? That means that you sort of broke this up into 3 different pieces, 3 roughly equal pieces. And you're going to see this occur at least once in each piece, I believe, right? n over 3 floor plus 1 is strictly greater than or equal to, is strictly greater than n over 3, right? Because this could be n over 3, I guess this is the floor of n over 3. It would have to be, or just, I don't really know, because yeah, well, n over 3 could be, it's got a integer part and a rational part, right? So there's some k plus some, I don't know, let's call it some remainder over 3, right? So, excuse me. Right, so the remainder could be 0, 1, or 2. If the remainder is 0, this is obviously true, right? This is just k plus 1 is greater than k. If the remainder is 1, you have a third, and you have k plus 1 is, yeah. So this is always, right, this is always greater. Yeah, that's what, yeah. So you're always going to have, so if you take each of these modulo 3, and then you're always going to have some remainder. It'll be at least, yeah, it's always going to be at least some remainder. Now, that's from the no, what could happen though is that this could be greater, even like this could be just this could be just divisible by 3, right? Like you could just have 2 extra numbers in there. You know, if you just had this going on. What I want to say is if you have bits that exceed divided by 3, I don't know, maybe just divide it by 3 then. Maybe you don't take the remainder. I don't even know. I don't even know. I mean, that's kind of, huh. Um, how do you even, I don't know. I'm trying to do this in just like some random test case. Gee. Some algorithm that seems to work for some test cases. So 0, 1, 0, 0, 1, 0, 1, 0, 1, and then 1, 0, 1, and 0, 0, 1. So somehow we have to discern that there's a 5 and that there's a 2. And both of these occur at least twice. Excuse me. Well, if there are 2 numbers that occur this many times, you would get overlap over the number of bits. Excuse me, but trying to figure out the overlap, I think, is kind of probably impossible. Probably. I want to say something like you can very quickly discern, though. You can very quickly discern whether or not, like you could very quickly find these numbers. That's what I want to say. Because there only could be 2 of them, right? Huh. We can figure out what the relevant bits are. Definitely. You know what I think we can do? We can try this. We can use count the bits, figure out that there's at least n over 3 plus 1 bits for a certain set, right? We can then construct that integer that has all those bits. And then I want to say something like all the numbers, I wanted to use that as like some kind of a filter to filter on numbers that sort of match those bits. However, no, that doesn't that doesn't work. Huh. Excuse me. Gee. Oh, it would be an or. You would get some number C, And then you have A or B equals C, right? Bitwise OR. Yeah, which is interesting. Of the two numbers. I don't really know. Yeah, because you don't have enough of the other numbers to actually get up there to get high enough, right? The other numbers it won't make it to get the bits in there. So it's guaranteed that this is going to be equal, right? However, now you have the task of finding these two numbers in your list of numbers. And it's possible, this is assuming that you have two numbers, exactly two numbers, at least two numbers. You could have the case where you only have one number, and then this kind of falls apart a little bit because there could be a lot of other bits that exceed this amount. However, that's because you've just got a lot of different numbers that share bits. And those could be disjoint from the bits that you're looking for. So you just get a whole mess of bits. You don't really have an obvious way to just discern between the 0 case, the 1 case, and the 2 case. We have 0 numbers that appear that many times, and 1 number that appears that many times, and 2 numbers that appears that many times. 2 numbers that appear that many times. I want to say, like, if you could find the 2 case and or rule it out, then you have some information to work with for the finding 1. And then if you can't find 1, then you have some information to. Then actually, if you can't find 1 either, then you're done, right? That's already at the 0 case. So you have something to work with if you do it that way. But I don't think it's. I'm not sure how to do that. I don't know if you can. Excuse me. Excuse me. Well, I want to say that if you could filter somewhat, and the numbers that don't have those bits, I guess, are not candidates. You know, in other words, if you were to OR A and this value that you got, this C, all the bits should be there, right? C shouldn't change. So you can eliminate a few numbers doing that. However, if you have two numbers, you have a lot of overlap. So maybe what you want to do is count the number of eliminated. Oh, here we go. Maybe you use that filter, and then count the number of numbers that were eliminated, right? So in this case, you actually don't eliminate any numbers from there. I think that means if you don't eliminate numbers, or if you eliminate less than what is this, n minus 2 times n over 3 plus 1, which is n minus 2 floor of n over 3 minus 2. If you eliminate, so if you add these two together, if you eliminate less than this many numbers, that means that you more likely than not haven't eliminated any of these, and it's possible that there's a bunch of numbers also that you didn't eliminate. So it's more likely than not you're looking at 2 elements to look for, depending on how many you eliminate. If you eliminated more than this difference, right, then obviously you can't have, it has to be 1 or 0. And in fact, if you've eliminated more than, what is this, n minus floor of n over 3 plus 1, then you're obviously in the 0 case. However, these aren't like crystal clear, because it's possible basically to not eliminate anything, or you don't eliminate a lot. It's possible to not eliminate a lot of things if you have in the 0 case. I want to say no. I think in the 0 case you can't. Yeah, you necessarily have to eliminate everything, I think. Yeah. Because, well, no, I don't know. You could have something like, no, because you're not going to have any bits that are, it's not going to be possible to have any bits that are is it possible? I'm just thinking of you like a mixture of bits. I don't know. How many do you? Let's see if we can think of a case where you have. I think we can do this. You have 9 numbers. They all have. Yeah. There's a way to do this where you don't eliminate too many numbers. Is there? One, two, three, four, five, 6, 7, 8, 9. I want to say you can do like this kind of a deal. And then we just need 4 of each bit, right? So this now has 4. This has, let's give you all zeros. This has 1, 0, 1, 1, 2, 3, 4. Let's give you zeros. 1, 2, 0, 3, 0, 0, 4. Pretty sure this could be done relatively easily. 1, 2, 3, 0, 0, 0. 1, 2, 1, 2, 3, 4, 0, 0, 0, 0. 1, 2, 3, 4, 0, 0, 0. And these are all different numbers, I think. 1, 1, 0, 0, 0, 0. And then 0, 0, 0, 0, 0. Oops. Like the last 3 ones. 1, 2, 3. And what am I thinking? Yeah, this could just be 0, 1, 0. Right. So these are all different numbers, basically. These are all different. This is 2, I don't recall what these are exactly. This is like 1, 2, 4, 8, 16, 32, 64, 128, 256. So this is like 2, this is 66, this is 128, 131, this is what, 8 and 32, 40, 168. These are all different numbers, so I don't think I have to actually go into detail, right? I think we got the idea. And the deal is, there's no duplicates even in the whole thing, right? But we would pass this test, this n over 3, right? Since there's 9 numbers, this n over 3 is 4, at least 4 bits. Every bit would pass, and so this filter, if we took the OR, it would pass. It would actually pass. Every number would would not add anything new. So that's kind of, I guess, a bit challenging. I'm wondering if there's a way to, in linear time, find out if there exists a pair. If you OR the 2 of them, you'll get this number, right? Because if there exists such a pair, then we can just count to see. Well, first off, we could figure out, is it always going to be a unique pair? That's one thing. If there's no pair, then we're obviously in the 0 case. If there's at least one pair, then we got to think about it. If there's only one pair, then we can just check to see how many of those, each of those pairs, right? There's only one pair, we just checked how many, see how many. If there's more than one pair, then I guess we're in kind of a strange position. But if there's no pairs, I guess what we'd want to do is, you may be in a position also to where there's one element that like, in other words, there is one element that there's at least n over 3 floor plus 1, but discerning that is kind of challenging with this value. So let me think for a moment. So let's suppose that there was a pair, and we wanted to know, okay, we wanted to find that pair, right? Well, first off, how how do we even find any pair, like just a pair, right? We would have to have I want to use a hash set so badly. Really want to use a hash set, but you can't because it's supposed to be linear extra constant extra memory. I don't think I'm gonna make this tonight, man. I don't know. I don't think I'm gonna see it tonight. I want to go to bed. Maybe I shouldn't have taken on this problem. If I got this in an interview, I'd probably wouldn't get it. I probably wouldn't get it because it's a little too challenging. I don't know. Bit manipulation stuff kind of can catch me off sometimes. I think given enough time, I'll get it. I'll figure it out, but I don't think I'd be able to figure it out in 40 minutes, whatever it is. I have to see a few problems similar to it before I would start to recognize it and see it and solve it quickly. Yeah, you want to find two numbers. If you OR them, you'll get C. By the way, very easy. Oh, wait a minute. Oh, you're kidding. Oh, I think I'm totally looking for the wrong thing here. Oh. Oh gosh, no kidding. You serious? Oh man. Oh, that's too funny. So, I think I may have figured out what I'm doing wrong, possibly. So there's actually there's another way to do this that's not linear time. Excuse me, there's a way to do this in linear time that uses linear memory using a frequency map. There's a way to do this in constant extra memory, but it's not linear time, by just sorting the list and then looking for each chunk, counting the frequency that way. Sort of do an iteration left to right to count the frequency after it's been sorted. There may be a way to do this that's that's linear time, that's technically sorting, but because you have two elements where a third of it is that element, you can actually sort this using a particular sort algorithm called the I think it's the Dutch flag sort, which would take linear time, and then you can use your frequency check. That's interesting. There may be oh man, I'm thinking basically what you would do is you would the Dutch flag sort I think usually has 3 elements that you're considering, but you could say like all the elements larger than a certain point, put them to the right. All the elements smaller than a certain point, put them to the left. And then I guess all the elements between these other 2 elements, put them in the middle. So you'd sort on like 5 different sections, something like that. The problem with that though is I don't think that works so nicely. And you may actually have to know what the elements are in the first place anyway in order to do that nicely. So I'm not sure if that works either. I want to say you could do something like a counting sort. You could do a counting sort. But that uses a frequency map anyway. I mean, that's like what that is. You could technically use a counting sort that doesn't have a. No, I think you have to use a frequency sort to do a counting sort. I think that's the only way to do it. Frequency map. Could be wrong about that, but I'm pretty sure you do. So, okay. All right. I think, I don't know, is there a way to do? Just thinking, how do you do a counting sort without a frequency map? I don't think you can. I don't think you can. Or can you do it? I think you have to do it with extra memory anyway. Even if it's not necessarily a frequency map, but something else. I don't think it matters. I was just thinking maybe like a linked list of indices where you found a particular element. Excuse me. No, I don't think counting sorts necessarily. Maybe some variation of counting sort. Maybe if you know what the median of medians does, I'm thinking maybe some variation of quicksort. Some variation of quicksort where you partition around a particular value. Where you kind of sort around a particular value. Everything to the left is smaller, everything to the right is larger. I don't think that really helps either, though. Because you might just have all the elements on one side or the other. Like it might not be all that useful. I think you have to do this using some bit manipulation. I don't think sorting is going to help. I was thinking maybe if you sorted it a special way, like all the elements smaller than a certain amount, all the elements larger than a certain amount. But No, I don't think that helps. I don't think that helps us. I want to use the bits to, I'm going to lay down and think about this. I really want to use the bits to create some kind of a filter, some kind of a mapping, some kind of a filter, some kind of a mapping. I really don't know though what it could be. So I got my laundry done here, so I've got some nice fresh clothes for the week, which is nice, which is great. Alrighty, let me lay down and ponder here. I don't know, man. It's got to be something to do with counting the bits. It's got to be. There's no other way. You know, there's got to be some thing involving that. But the question is, what? What do you do? Yeah, I mean, dividing by 3, or rather dividing by that, you know, n floor of n over 3 plus 1 would give you at least 1 for the bits that are of interest, at least. However, you might have bits that are not interesting that are also 1, or bits you don't necessarily want to think about. And then you could also have bits that are greater than 1 because they belong to both of these numbers that there are many of. And as you saw, you could have an instance where all of the bits appear to be, they might be interesting or relevant. However, there are no duplicates throughout the entire array. Also, got some irritation on my skin here. I don't know what that is. Now, I wonder. Excuse me. Oh, you know what you could do? I got an idea. Aha. Oh, wait. Maybe not. If you... I wanted to say something like, no, because you don't know how many times these things appear, these numbers. You know that they appear at least a certain number of times, but you don't know, or potentially, if you suppose that they appear a certain number of times, confirming that, Oh shucks, I was gonna say there are things you can do if you know they only appear 3 times. You know if they appear exactly 3 times, or exactly some multiple of 3, or if they appear exactly some multiple of 5 or something like that. You can do some interesting things with bit manipulation. I don't really know how many times these numbers appear though. You don't know. They don't appear a certain multiple. They appear more than a certain amount. Well, you know what? You could check to see if they appear. Shucks. That's kind of hard, isn't it? Hmm. Hmm. By the way, this also has to, whatever algorithm I come up with, has to work on the test case where you have 4 9s and 5 zeros also, which would be an interesting scenario to consider as well. If you have zeros in there, how many times does 0 pop up? You could, I guess, handle that test case separately. You could just eliminate all the zeros. Just do one pass to see if 0 is relevant or not. And if it is, then consider it and sort of, basically skip all the zeros. The other considerations, I guess, something like that. Well, actually, the zeros will get skipped anyway. Hmm. Wondering if you can break your array into 3 different pieces and think about those 3 different pieces and break them into floor of n over 3, 3 floor of n over 3 pieces, and if n is divisible by 3, you'll have you'll have 0, 1, or 2 elements left over on the right side, we'll say. And let's say if you have a number, then it's got to appear in it's got to appear in one of those, right? Well, it could be, depends on what the remainder is, I guess. If the remainder is 1, then it has to appear in at least one of those sections. And right, I'm using pigeonhole principle here. You could fill n over 3. You could fill one segment, and you have one element left over, and that could be in one of the other 2 pieces, or it could be one of the remaining elements. Now, if you have 2 of such duplicates, you have a similar thing where there's one that will contain it, another one that will contain the other with certainty, and then there could be, the element could be, both of the elements could be the remainders. I guess it depends on what the remainder is. If you modulo 3, you divide by 3. The thing about that though is I'm not sure, knowing that, if that's any value to us, because, like, I don't know, I guess we need to, I guess you need to find elements that are common, that are just present in both pieces. N over 3, the first N over 3 and the second N over 3. And huh. Man, I don't know. It's got to be something with counting the bits, total number of bits present. It's got to be. The number of bits that are present. Oh, wait a second. You don't have that many bits to consider. So you could just remove a bit. Like you could try to just do bit by bit and try to figure out which bits are relevant. How would you do that though? Could you remove one bit at a time? Well, you already counted all the numbers that have that particular bit, but then you want to, I guess, take the elements that have that bit, the numbers that have that bit, and then not just count how many there are, but I guess how many of those elements are equal to each other? Something like that. Huh. Yeah, I guess. Yeah, I guess you could do bit by bit and do it that way and figure out of the elements that have that bit, how many of them are equal to each other. Well, what does that mean? Like how many? What would you want to know? Yeah, you'd want to know what's the the highest frequency of those elements that has that common bit. Yeah. And does that exceed, right? Or are they all different? Something like that. So you'd want to, yeah, you'd want to know the highest frequency. If the highest frequency is not the floor of n over 3 plus 1, if it's less than or equal to less than that, then you eliminate that bit. That's not a relevant bit. So we can get rid of, in theory, we can get rid of all of the relevant bits one by making that check to see. But then we have to do a frequency check on all of the numbers that have that bit, right? Which, I mean, you could technically you can do that in linear time and linear space, but we're trying to do this without linear space, right? So how could we do that in constant space? A kind of a frequency check on the elements that only have the first bit, let's say. And then what would happen is, I guess what we would do is, do a bit check again, a bit count check, right? Count all the bits again for this subset, right? And if a lot of these numbers share, I guess what I want to say is, I want to say something like, we could have the same situation sort of over and over again where all of the bits have the same bit count, right? So like if it was just the same number over and over again, right? Each bit that we check, we would get the same numbers every time. And this should be fine too, because we do, it's one pass for every bit, and then no. Yeah, every bit we would pass through every number, and then for every bit and every number we perform a count. So it's a constant times the total size of the it's a constant times the total size of the actually, something ironic about this, by the way, it's a constant times the total number of numbers. Oh no, oh never mind, it's not that ironic. I take that back. Times the total number of numbers, and then you also have a situation where if you performed a similar routine on every subset that had a particular bit present, you would still end up with a quadratic, you'd still end up with a constant, you still have linear number of passes because you have this constant squared, so it's still a constant, relatively small constant too, even though it's squared. Although that number is getting, it gets pretty big, right? If you take 32 and square it, no, that's a pretty big number. I think 32 squared is, I don't know that offhand, 2 to the 5th, 2 to the 10th, 1,000. Yeah, it's getting bigger. It's quite big. It just occurred to me why the input size. I was thinking about the input size. It's a linear algorithm on an input size that's like 10,000, and I'm thinking to myself, why would they only be 10,000 if it's linear? And the reason for that is because you're going to have a big constant in the front, because you're probably going to do what I just described, which is then on each subset that shares a particular bit, you would want to know which of those bits are still reach that what do they call that? Still reach that test, that condition, and you can eliminate elements from consideration. Now that's tricky too, because you have to keep track of which elements you've eliminated, which is, you know what you eliminate? You don't eliminate elements, you eliminate bits. You figure out which bits aren't relevant or not. So obviously the subset that has, so each bit, when you examine the subset, that particular bit itself will stay, potentially stay. However, so that's how you would I think that's how you eliminate irrelevant bits, right? And then you end up back in the situation where you have potentially two different numbers that are relevant, and you take the quote-unquote OR of those bits, and that gives you the this sort of total number of relevant bits that you know belong to what you're looking for. Now, I guess what's interesting is, yeah, you basically eliminate all of your sort of duplicates that way. Not duplicates, your extra value, extra numbers that we don't care about. Right, you get rid of all those bits. You throw those all get thrown out. However, there's still an issue of like, well, what if you have a bunch of zeros in there? That gets really confusing. The zeros will get passed over if you. They're pretty much going to get ignored completely, passed over if you're looking at they'll get completely passed over if you're looking at excuse me. Also, I'm not sure how this works with the negative values, negative numbers. I can think about that too. But zeros will get completely passed over, I think, if if you are just looking at the bits, you may just want to do one pass to count how many zeros there are. I think all the logic stays the same. You can figure out which bits are relevant and not relevant, and then you've got to decide between, okay, do you have two numbers or one number? Once you've gotten a list of all the relevant bits. So in our case with 2, 2, 5, 5, and 1, when we take a look at the bits, the set that has ones in it, the first bit that has ones, you have 1, 0, 1, 1, 0, 1, and 1. And so that bit is going to be relevant right there. And then the second bit is not relevant, and the third bit is relevant. So you don't have the second bit anymore. And then so you skip the second bit, you take a look at the third bit, and you say, okay. So actually, I think if you do that, what's going to happen is you're going to discern one of these duplicates. I think that's how that's going to happen. Or alternatively, you can realize that the first bit is not relevant because something got eliminated. So maybe you eliminate that. No, I don't think that makes sense either. I don't know if that even makes sense what I just described. I want to say you do some kind of round robin bit by bit after you've kind of discerned which bits might be useful. What you might end up with is, yeah, so okay, so if the bit you're looking at is part of one of the groups that have one of the subsets of numbers that does have you know, a whole bunch of duplicates in there, you know, the right number of duplicates, then the relevant bits will be somewhat exposed, I guess, there. However, the bits for the other set, I believe, will be removed. No, the other set could be. They both could share a particular bit, but if you go through all of the bits, you're going to hit a point where one set contains that bit and the other set doesn't. And I mean, that's maybe a way to discern which ones that you care about, I guess. Which ones are shared? Well, you possibly already know which ones are shared. Maybe you can figure out which ones are shared and which ones aren't. Oh, it's just so tricky. It's so confusing. So so uncertain because there's bits that you don't care about at all that you want to get rid of, and then there's bits that are sort of interlocking, right? Where you know, like 1, 0, 1 and 0, 1, 0, right? Like 2 and 5, where those bits interlock. Some of them are relevant to 5 and some of them are relevant to 2, but they're not relevant to each other. So they're kind of mutually exclusive. And then you've also got the bits that are, you know, if you had like, if you added, I guess it'd be 8 to these numbers. So if you had 10 and 13, then there would be bits that are shared between 10 and 13 that are just shared between all those numbers. Oh man, and then you could also have a whole bunch of other numbers, you know, relevant numbers that just have bits all over the place, that even though you have 4 of every bit, they're not a part of any of the numbers that you're looking for. Gosh, man. I really want to go to sleep though. I don't know. Gee. Also my shoulder, ouch. My shoulders are both kind of banged up from the muscles are kind of torn up a bit. The somewhat damaged because of what I had done. I had muscles are somewhat damaged because of I had used them kind of too much, we'll say. Just used them too much, my arms, shoulders. Really hope it heals and doesn't ache so much in the future. I want to, a small, very slight sprain on both my shoulders, but I hope hope it heals okay, because I don't want to have this like ache for the rest of my life. That would be unfortunate. Seeing as I'm already 28 years old, I'll be 28 in a few weeks. It's like, man, I don't have a lot of years left to live here. Like I don't want to be aching the whole way through already, just from this one thing that I did a few weeks back. That would be really unfortunate. My dad had mentioned to me when I was younger. He was like, "Yeah, man, I did something to myself when I was younger, and it aches forever now after that." And man, I love my dad. I really miss my dad, but yeah, it's like, gosh, my memories of him, it's like he's still here. Feels like I took my dad for granted, Gosh. When I think back on those memories so long ago, when I was at university, gosh. Oh man. Sorry, I'm just thinking about my dad. Kind of had a flood of bunch of memories just came back to me from when I was younger, much younger, 7, 8 years ago. Where I was, what it was like, where I was in my life with my dad. Gosh. Yeah, forgive me, I'm tearing up over here. It was just so different, my life was just so different 8 years ago. Let me focus on this problem. I can go back to think about my dad later. So you do one sort of straining through of all of the numbers, and then you could do another kind of a straining through each bit. You can use each bit that's relevant as sort of a what do they call that? A subset. And for each of those subsets, you would, I guess, strain down again to only the numbers, only the bits that have at least the floor of n over 3 plus 1 values present. And I think what would happen is, if there were two such numbers, eventually doing that quote-unquote straining process, you would remove all of the bits, I think, or you would remove a lot of the bits. When you consider each subset, I think you would end up removing all of the bits until you get to exactly one of the relevant numbers. I think that's what would happen. So like, let's say, okay, so we did for 2 and 5, or 2 and 5, you would remove the second bit when you're considering you consider the first bit, you remove the second bit, and then you skip the second bit because you removed it. You consider the third bit now, and you keep that, the third bit, and that's it. And then that's 5. and then you can say, okay, we're gonna do one more. We're gonna now remove all of those relevant bits, and then do the same pass again that we just did, where we go bit by bit, removing every bit that doesn't matter, I guess. And then you should get the other number, I suppose, or you'll get 0. Yeah, that's interesting. You work on every one of those subsets. I think that does it. That gives you a constant of like 2000 in front, and you basically either end up with 0, which means none of the numbers survive, none of the bits survived, and that gives you either none of the bits survived, and that means there are no numbers are satisfy, or you have one number that survives, and then that's it. That's the only one. Or yeah, you have one number survives, and then the second number the second time, the second pass gives you 0. That means you only have one number, and then the first pass and the second pass give you numbers, and then that's it. And then you found both of them. And you do have to do one pass through for 0, because you may have the case where none of the bits survive. However, 0 is one of the considerations. I think that's the only like edge kind of scenarios. You just have to consider if there's a 0 is relevant there or not. That's it. Yeah, you kind of just obliterate all of your bits by running through a bunch of passes, and I think that works. That would give you constant space and linear time. I think that's it. Definitely quite the algorithm. I don't even know, coding it up is going to be kind of funky. Excuse me, but yeah, maybe I should have solved the problem first, and just like very quickly, use the frequency map, and just wrote that just to show you what that is, just so I could say I solved the problem. You're already at like 10 o'clock. I want to go to bed. I don't even want to code this up. I just want to go to bed. So we get a frequency map, which is unordered map of int frequency, say for auto x and nums. What we're going to do is take frequency of x, and we're going to plus, and then we're going to take for auto p in frequency, and we're going to say, I think you can actually do something like this, which is it's going to be value frequency. Occurrences, I guess. And I don't know, num or n, val n, we'll say. And we'll say if n is greater than or equal to nums.size divided by 3 plus 1, or it's just greater than, we'll say. This I think does integer division already, so I don't think I need to do anything extra. Then we'll have vector int ret dot push back the value. So I think this is the sort of standard approach. This would be like the easiest way to do it. 3, 2, 3, 1, 1, 2. There's always at least one number, and you can have negative numbers. Let's try it. Okay. So yeah, this is like the, the really straightforward way. Now there's a way to do this that's way more complicated, which is what I was just describing. To do it with constant space, which is we're going to use, first we're going to say count the bits. So we're going to do for auto x and nums, for int I equals 0, I is less than 32, plus I, say int which equals bit shift to left I, and we're going to say standard array integer 32 count, or a bit count, and you say bit count of I is equal to plus equals 1 less than I and x initially. And we're going to say determine bit by bit which bits are, okay, I want to say determine relevant bits, relevant first pass. We'll say for I equals 0, I is less than 32, if bit count of I is greater than nums.size, let's just say int target equals nums.size divided by 3 plus 1. I'm actually going to do it this way. First pass of I equals this. So these are the relevant bits. If your bit count is greater than or equal to this target, that means you're irrelevant. Determine the relevant bits. Make another pass for each bit on each subset. Pass on the numbers filtered by each relevant bit. i.e., make a pass on a series of subsets. At least one relevant bit, initially relevant bit. Right, if that makes sense. So for int I equals 0, I is less than 32, plus I, which is going to be I 1 less than I, say if first pass of I, now we have, by the way, a second pass, or just array boolean. We'll call this, or we'll say int still relevant, I guess. So we'll say which, if first pass of I, then we're going to do another pass, which looks like this. Each time we'll set up this array here. We'll say standard array, another bit count. Let's just say count this time around. Count each number in nums. So actually, we want to say yeah, okay, it's kind of funky, but it's for each bit we're going to do this, and we're going to select that bit, and we'll say if first pass of I, then that bit is a bit that we care about. Then we're going to say we're going to have this count array, and we're going to say for each number in the numbers, if which and x, then we'll perform the following. Which is to say, count the bits, which we have, we'll just call this, I don't know, y, maybe. All right, so we count these, so these bits we set to 0, initially 0. I think there's a way to set this to initially 0. It's just array cpp ref. Constructor. I just wanted to 0 initialize. Okay, gotcha. I want to 0 initialize the, like, how do I initialize an array to? Find the rules. And we could fill, but I don't really want to do that. Interesting. Make array. Oh, that's kind of interesting. Wow. You know, huh. I don't know. I want to say it starts off at 0 initially. I think they do. I just wanted to make sure it's initialized correctly. I mean, I could fill it too, just standard fill, you know. Maybe I'll just do that. Fill with a value. Yeah, I'll just to be certain. We can come back to that. And then let's count. All right. So for each number, if this is there, that number, so this defines the subset, then we're going to increment that count of now this is actually going to be right. So this is kind of interesting. So it's and these two values. Yeah. Call it J. Let's see, this is kind of interesting. And we'll call that Y. Right. Sort of a double loop going on here. Yeah, very interesting. So what's going on here is you say and Y if so you're going to say for each I you have some value which, and then you say if that's relevant, then we'll continue. And we're going to count, we're going to pass through all the numbers and collecting a count. And we want to say only care about the numbers where X is relevant. So really it should be if which and X, then we only care about the numbers where X is relevant. And then we say for all of those numbers, we want to check on for each Y, we want to count Y. And we say if which and Y, and then we're going to increment the count for J. And actually this should be this is actually incorrect. The bit count we should increment by 1. This surely should just be, this is non-zero, right? It'll be true or false. Yeah, you want to do this. I think it'll work correctly if you do it this way. Yeah, you want to do the same thing here. So you want to just say it's non-zero. So which and y? Okay. That'll give you, so this should give you the first number. If we take this count now, and we'll say I guess first instance, call it 0, and we'll say for int I equals 0, I is less than 32, plus I of this count. Oh, no. Okay, wait. I want to think about this here. So, no, we did this wrong. So we have to build this still relevant, right? And you also want to see, right? So if it's in the first pass, the things that are still relevant are going to be. The thing about that, though. I want to say something like n still relevant. And which is still relevant. You know, that's kind of awkward too, because negative numbers are involved here. So I'm using greater than 0. It's very, it's a little awkward. I'm actually not sure how this works with negative numbers. I didn't really think about it. You can just say not equal to 0. That's probably better than greater than 0. This actually should be, you could do that, I think. Or this. Hope I could do that. Or not 0. How do I get it's like -1, right? I don't remember what this. You flip all the bits and add 1, right? If you want to get the negative value, you would subtract 1 and flip all the no. Yeah, you subtract 1 and flip all the bits. I want to say like negative int max too. There's like so many ways to represent this. It's int min. Oh boy. Let's do that. Int min. Numeric limits. So we do numeric limits int and then min. Standard numeric limits int min. There you go. So every bit is considered still relevant at first, and then so we say if not first pass of I, then still relevant. How does it go? So if it's not in the first pass, then still relevant, and then we can actually continue. Then you just have to update. You have to and equals itself with which, with not which really. Or you know, whatever that is, the bit flip. No, I don't think we can just flip like that. It would really have to be, well, we're going right to left anyway, right? So it'd really be just, you could just do XOR. It's better. Yeah. All the zeros won't do anything, but the one will flip. So it's still relevant. And then you say, so if first pass and oh, no, it's gotta be, no, that won't work. Shoot. How do I, oh no. How do I flip this just that bit? You can grab this again, I guess. A lot of bit manipulation going on here, but if you do XOR these two, yeah, you can do that. So this is all zeros and a one in a particular spot, and all zeros everywhere else, and then this is just all ones. So if you XOR this, all the zeros and ones will still be ones, but the one in one spot, this one spot here will turn into a zero. So that's what you want. You want to AND equals that, so that turns it to zero. Okay, got it. And then, right, what we're going to do is we also want to check that it's still relevant at that particular spot is not equal to zero, right? So this kind of, by definition, the first pass will be, yeah, because we actually want to update still relevant if this doesn't work. So we'll skip this whole part. Anyway, we continue. So we take these two, and it's not equal to zero. Then we want to count and figure out which of these are still relevant. Yeah, so we apply the filter using which on all the numbers. And again, it's got to be not equal to zero. And then we say for each bit in that number, we're going to increment the count. Again, not equal to zero. Okay. All right. Gosh. Yeah, well, we don't even need this then. We don't need the if statement. We just, there it is. Increment the count. Okay. Now, the interesting part down here is for j equals 0, j is less than 32 plus j, say if count of j is less than the target, and then we're going to update still relevant. We're going to set to 0. We're going to do this. Not with which, but with j. 1. Alright, this looks real funky, I realize. But that's gonna, so still, what remains is still relevant. In theory, must be either all zeros or if there are no elements that appear target number of times, or the first element appears target. Yeah, target number of times. Okay, so I actually want to print still relevant. I want to test this theory here on some of these test cases. Some nice compiler errors here. Numeric limits. Numeric limits. Excuse me. Oh, is that why? Yes. I mean, maybe you should just say int all zeros. So I don't have to call it. It doesn't matter. That's fine. Or all ones, rather. Should be fine. Nice compiler errors here. Reference to overloaded function. Can be resolved. Oh, you know what? I shouldn't use the word count. I should be. This actually should go inside here. And I really shouldn't use the word count. It should be like, just call it bit count again. It's fine. It like overwrites the previous context. So yeah, it's pretty interesting. Right. Huh. 0. Oh no. No. I'm expecting 3. And the hello should be 3. It should basically hone in on this algorithm should shave down to one of the two elements. Just thinking if actually for 3, 2, 3, you have like 1, 1, 1, 0, and 1, 1, and you're looking for 3 divided by 3 plus 1 is 2. So the first bit, you see it, that subset, you would keep all the bits. The second bit, that subset, you would keep all the bits again. So you should keep 3 here. You should get 3 here. The reason we're not getting 3 here though is strange to me. I'm not sure why exactly. You could print it at each pass, I guess. Also, I gotta close up some things before I go to bed. Yeah, okay. It's all 1s and then suddenly it's a 0. That's not right. Why? Right, so this should be 0 most of the time. The first 2 bits should be relevant, and then after that you should see check the whole way down. It's like 30 times, right? Okay. So what do you have? You have which and still relevant, not equal to 0. So we enter here, this bit count, fill with zeros, say, okay, for each number, if the number and which is not equal to 0, which I think for the first number, which is 0, right, or which is the first slot, this should be 3 and 3 twice. And you would say, take a look at the bits through 3 and 3 again, and you bit count, you would have those 2 spots for the bit count. The first 2 spots should have 2 and 2. And then you would say, okay, afterwards, if it's less than the target, then it's no longer relevant. which value moved 1J. Oh. Well, yeah, value moved. I guess we'll just put J in here. Okay, so that's pretty interesting. So this didn't get touched. And also kind of interesting is this didn't seem to do anything. How come this didn't do anything? And also, so there's a 4 here. Okay. So when you AND equals this with this, that should remove the why is this not? I'm very confused. Very, very confused. And we're going to try to see how this goes here. What happens here? Okay. It doesn't seem to affect this at all, which doesn't make sense. Because this is basically removed 4. Which you could, or added 4 really, which you can see. And that should actually cause this to add a 4. That's really confusing. It's supposed to be performing a bitwise AND, but it doesn't seem to be. Very confused. Why would that not perform the bitwise AND that I'm expecting? What is going on? Huh. Excuse me. It is a bitwise AND, right? Yeah, must be. Like 5 and 3 should give you 0. Oh, excuse me, 5 and 2. 5 and 3 give you a 1. My mistake. Yeah, 0. So, okay, what about -5 and -2? What does that give you? -6. Okay. What about standard numeric limits of ints min and -2? What does that give you? Okay, that's interesting. I don't understand at all why that would be the case. That doesn't seem to make a lot of sense to me. But if I took this number, oh man. And I tried that. I think it would work. No, doesn't matter. What? What do you mean? What? Why though? What? When does this stop working? When does this stop functioning? I'm so confused. Isn't this just all ones? Isn't this? What if we do that? What is going on? Huh? There's like some point where this just it just gives up. It's just like it doesn't work anymore. That's it. I guess what you mean to say is that these bits already agree with each other on which ones are 0, which ones are not. But this should all be 1s, and oh no. Maybe that's what I'm missing. Maybe I don't realize something here. Maybe that's the problem. Maybe the problem is with me. I don't realize something important. How do I show that this is signed? Oh, maybe it's... No? I guess assumes there's a 0 in the front. I'm very confused. How do I get a... negative and literal? Don't mind me. I finagle with this. Excuse me. How do I get a -2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. 32 bits. If I just make one of these a 0, no, it's being interpreted as a... if I just throw a bunch of 1s in there. No, 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 what? Oh, what is going on? I don't know. How do I make this thing negative? How do I make this thing negative? I don't remember. Oh, I just did this the other day too. I thought it had to be all 1s. Excuse me. Alright. Let's say we want -1. What do? We flip all the bits and add 1, I think. Or no, we add 1 and then flip all the bits. So like 1, 2, 3, 4, 5, 6, 12, 18, 24, 30. Alright, I think that's 1. Okay. Now if we do the same thing, flip all the bits. 1, 2, 3, 4, 5, 6, 7, 8. 16, 24, 32. Alright. Flip all the bits. And then add 1. No. Add 1 and then flip all the bits. No. Can we do this? No. Huh. I don't know, man. I don't know. Like, shouldn't this be something, though? And then just a very large... Why is this being converted to a long? This is driving me crazy. Or unsigned. First digit is the most significant. It's driving me crazy, man. What does that mean? The first one is the most significant? What is that? We got negatives the other day. We figured it out before, but now I can't seem to get it right. What did I do? How did I do this? How? What? What? Also, which ones are most significant? If we put this here, a 1 here, what do we get? Okay, so the leftmost is the most significant. All right. Do we not have enough bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Pretty sure you have 32 bits. What if we did one less here? Okay. So that threw a 0 over here. What about this one? Still a 1. Okay. So we take off another 1. Okay. Oh man. Why are these positive numbers? Why is this happening? Oh, I just want to go to bed, man. Oh, I think I have to, I don't know, like cut the stream, end the stream here, go to bed and come back to this later or something. I really wanted to finish this before I went to bed because I wanted to keep it one stream, you know. I really don't want to like split it into 2 pieces. That seems so bad. I mean, I guess it's not that big of a deal. It just part 1, part 2. I really don't want to be doing that though if I can help it. Why can't I get negative binary literals? Ah! What's wrong? Why? I'm so confused. Oh, there we go. Okay. So that's really weird. That's really interesting. So for some reason this gets placed into an unsigned integer when used as an argument here. However, if you put it into an actual integer, then that's so strange. Maybe that has something to do with it. I thought about doing that where That might be why. It might have something to do with it. Well, actually, I don't really know. Maybe this has got to be converted to an int. Maybe that's what I'm doing wrong. Maybe it defaults to an unsigned int, depending on the context. That's why I'm having some issues. Okay, not making a lot of sense here. I don't know, man. I'm so confused. Why? Why? Maybe, alright, so this is -1, by the way. -2 would be, so -1 is flip all the bits and add 1. -2 would be flip all the bits and add 1. Is that -2? Yeah. And -2147483648. So actually, I have this wrong. That's probably why. It should be -1, not all ones. It's actually -1. Whoops. Whoops. Yeah. Okay. Well, about that. That would explain some things. Okay. That's good. Glad we cleared some of that up. No kidding. Gee. Okay. -1 initially. And we have this still relevant. Now it's 0. Value removed. 1 through 31. By the way, is this again? 1, 1. Okay, not quite. Better, but not quite. So everything got removed from 1 to 31. Now that can't be right because 2 shouldn't have been removed. Hmm. Target is num's that size divided by 3 plus 1, so it's 2. Okay. So if the target is less than 2, or bit count is less than 2, which I set the bit count, oh, that's why. Oh. Oh, that's confusing. Okay. X and Y, alright. That's pretty funny. Relevant value is 3. There you go. We got 3. There we go. Oh, this is some funky code, man. It's just not very, I guess, legible, I want to say. Maybe I should have used better variables than X and Y. Oh boy. So, let's just say current num, and which bit, let's say. Or let's say filter bit. Really could have used more descriptive variable names. So the filter bit's still relevant. And then we have its current numbers. Say if filter bit and the current number are, if, right, filter bit as a part of the current number, then we'll just say bit shifted, or just, call it Y. And now we can use current number. So if Y exists in that current number, then we can increment the bit count. There we go. Yeah. So now, okay. Now we can remove these relevant values. Okay. So yeah, we get in each of these cases the first one, right? 3, 1, and 1. 3, 1, and 1, as expected. Yep. No. That's okay. Gosh, man. Don't mind me. I don't use 2's complement often enough to really Don't do enough bit manipulation to be able to do this stuff really quickly. Now that should give us, every time will give us the first relevant number. Now what we can do is actually take the, do the same pass again. However, this time skip the bits in the first number that you found, if that makes sense. So we do the same routine again, except we skip some parts of it. All right, now so we say if still relevant is not equal to 0, then make yet another pass. The number is filtered by each relevant bit, although each relevant bit so this time filter out number discovered above if one has been discovered at all. So actually we can make this a subroutine, this thing. And we can say int found equals, so if still relevant is not equal to 0, we can say if, so int found equals still relevant, and then we can say from the first pass, right, we have so still relevant, then equals -1 again. Literally the same routine as this. Let's just set this found thing here, and then we want to XOR this with what's been found. And we also want to put standard vector, call this one temp for now. Let's push back what we found. We say still relevant, we remove anything that we've already, whatever we found already, and now we do the same routine here. And we should find the other number now. And then we would say if still relevant is not equal to 0, then temp.pushback still relevant. And then we can swap ret with the other. Excuse me. Excuse me. Oh. You can return temp instead of ret. 3 and 0, 1 and 0, 1 and 2. Interesting. Right, so there was no, right, okay. Yeah, that's what you expect. Okay. And let me just wipe my face. Yeah, I think I would want to make this a subroutine. This whole function here, this whole thing. And make this an argument. Something like that. It's fine to sort of write it out this way. So now we would return temp instead. Then we can get rid of these debug messages. Excuse me, actually get rid of this whole thing. Now the question is, oh, what happened? Oh, I got rid of too much. Still have to handle the edge case for zeros. So we'll say, oh no, I think actually this says there's no zeros in there. Oh no, there could be. Special case. This would make this ret, I think. Yeah, because I think you could run into a position where you have a bunch of zeros here. Right. Moment of truth here. Okay, looks like it's working. Let's see what happens here. Nice. Works. Almost can't believe it works, but the theory was correct. Wrong answer. Ooh. Okay. Ouch. Nope. Okay, that's unfortunate. Dang. Dang. I thought that might happen. Darn it. Not correct. I'm wondering if I just need to perform a single check to eliminate this case. And all you gotta do is just run a one search on what you think you found, and the exit if it doesn't work. Because if such a number exists, it's guaranteed to come up in this with this filtering. It has to come up with this first filter. Now you could get a false positive though, so that's all you have to do is just check for a false positive. I guess that's the only thing. Check for a false positive. Can actually use there you go. That handles false positives. Oh, expected 2, output 0. Uh-oh. Uh-oh. What do you mean? What do you mean? Uh-oh, this should have worked. What happened? Huh. No, this had to pop up. Definitely had to pop up. You got a 1 at the end? That can't be right. That's not correct. How? No, that's definitely, there's 1, 2, 3, 4. 2 should not disappear. How did you get a 1? That's not correct at all. It's just misprogrammed. I don't know if this is the correct algorithm though. I think it is, but we will find out as we continue. Learn more. Output expected. A 1 somehow over here. That doesn't seem right. So it's first pass. By the way, I could change this first pass to an integer. I think that might be better, easier to work with if I do it that way. This is probably easier. Yeah, you could do something like this. Okay, that's a lot better. Then you can just say really it's just the first pass initially, and you don't need to filter on this filter bit. And you would say first pass and filter bit. If that's 0, then we would continue. Skip. I think that's the only part where we care. Yeah. Okay, that works properly. Why though? If the filter bit and it's still relevant, then we're gonna do a count over all the bits and all the bits that share that particular the bit of interest, we'll say. What I want to say is maybe we don't need to eliminate all of the Maybe we only eliminate the bit of interest, not all of these. Yeah, this may be wrong. If we're missing, yeah, there could be some mismatch between some of the bits and no, you won't lose. I think you have to be careful not to come back to any of the bits that you've already visited. Yeah, that might be it. I think you got to start off at this filter bit. I think that might be what's wrong. No, really, it's too much, huh? How is that possible? That doesn't make sense. What do we get for the first pass? Three. Okay. And then you say, all right, get this bit count, and you say j equals 0, j is less than the target. So of the bits that have a 0 in it, 1, or have a, yeah, the bits that have a 1, which is 1, 2, 3, 3, 1, 3, 4 doesn't have it, 5 has it, and 9 I think has it as well. Okay. We would conclude that you keep 1. I don't think that's right, though. No, you do need to go back to the beginning. So you would keep 1, but you wouldn't keep 2, because 2 doesn't exist. Oh, that's interesting. Oh, no. Uh-oh. It's possible to get fooled here. No. So this is the wrong algorithm as well. Yeah, I think it's wrong because, as shown here, right, you can get, oh gosh. You can run into a problem. Where you keep the 1 bit and remove the other bits. Something doesn't seem right here. I think there's more to this that you've got to do. Removing all of the other bits I think is a bad idea. Excuse me, yeah, because they might already be removed. Oh, so you have to only consider, I think you only consider that particular bit. Um, I think I got it. For each bit, there will be a number, which is all of the bits that are duplicated, or all of the bits that reach the target for that particular, for all the numbers that share that bit, filter on that bit, you want to get all the bits that reach the target. So, and that'll create a number, right? So every bit has a number when you filter on that particular bit. So this first bit, you'll get a 1. Second bit, you'll get a 2. Third bit, you'll probably get probably 0, I guess. You probably get zeros for all the other ones. And then what you're going to want to do is, I guess, you test each of those numbers to see if those meet the target. You do them one by one, and then you return those. I think that's what you do. And obviously you're going to get a few duplicates in there, but that'll give you 32 numbers to operate on. I think you can do it that way. Let me try that. Let me write a subroutine that's like a filter routine. It basically takes advantage of with this idea here. Excuse me. I'm actually gonna make this a set. No. So we don't actually necessarily care about first pass. What do we care about? We care about something like this. I want this to be in a subroutine. It's going to return an integer. So what we want is there's some int, which bit, or bit index, or just index, call it. And we're going to say that's the filter bit. Don't need this anymore here. Now we're going to say if filter bit and still relevant. So still relevant will be -1. And we'll say if this filter bit and still relevant is not equal to 0, which it won't be in this case, so I don't think we need this. We can say bit count filled with zeros, each number in the numbers. If the filter bit and the current number is not equal to 0, right? So this filters on the numbers, and then this will give you. We'll loop through all the bits and increment the bit count, and then for all of the values that are below the target, those aren't relevant. Alternatively, you can say filter bit I, if this is greater than or equal to the target, you can, or equals 1 bit shift to the left with J, right? Yeah, that's pretty much what you want. And then so this is going to give you 32 different numbers if you filter by bit. Make a series of passes on the numbers filtered by each initially. Make a pass, a series of subsets, at least one initially relevant bit. So now we can do for int I equals 0. This is actually going to return still relevant. Also, this can just be right. So that'll return a value of a number that seems that might be relevant. So for each of those, you have filter by bit. If first pass and this index are not equal to 0, okay, so first pass and this bit are not equal to 0, then you're going to want to filter by bit on that index I, and that gives you possible match, right? Now, what you want to do is Can make this a subroutine also. Auto check match, call it. And we'll say int val target. And we can also do, yeah, we'll use a boolean. So pretty much all of this just goes up. Check is 0, x and nums if x equals val. Increment the check, the check's for the target, return true. Otherwise return false. Okay. So let's check match for some value. So if check match of 0, then we're going to say temp.insert 0. Could call this ret now, I think. Filters a subset of the given integers. Oh, I think I also need nums here. Probably need nums up here too. And these could be one more over, yeah. Terminal, this filter subset of the given numbers. A bit and performs and filters again. Further numbers on the bits reach on the number of bits on the bits from that subset that reach the target. On the frequency. Have a frequency occurrences. Is it ents or a-ents? A-ents or e-ents? Occurrences that reach the target. Okay. Now, series of passes. Pass on a series of subsets, reaches subset, contains at least one initially relevant bit. Then attempt to match the resulting numbers. The whole, I guess, array. So now I have this possible match. Now we can use this check match of possible match. And we can say ret.insert possible match. Yes, it's a super simple routine now. Let me get rid of the rest of this. That matters anymore. And finally, we can return standard vector ints. That's going to be ret.begin, ret.end. Is that right? And that should be index, not I. I don't think I use that anywhere else. Just there. Hey, now we're correct. Okay. Yeah, I think we got it. And I'm fairly certain that's still linear time and no extra and constant extra space. Yeah, because this gives us 32 different numbers to match on. And pretty interesting. One of these filters has to contain, each of these filters has to contain the numbers that we're looking for, necessarily, right? Or at least some, yeah, the numbers we're looking for must be present somewhere in one of these filters. Yeah, when you filter on each bit, you basically say, okay, we're going to get, all of the numbers that, from that bit, all of the numbers that have that bit, filter down everything, all the bits that don't meet what we're looking for, and that'll give you some number. Now, there may be cases where this misses. I don't know. I don't think so, but somewhere in there you're going to get the two numbers that you're looking for. Let me just think. The reason why would you fail in some cases? Before I hit the submit button here, I just want to think about the maths. So you're going to at least, like, you're definitely going to, somewhere in there, you're definitely going to get a number that has all the bits that are relevant. The problems you might run into are like, well, you're going to see this, you're going to see the same number over and over again. Because let's say something has like multiple bits, right? And that's the number you're looking for. If each of those subsets, there could be other sort of quote unquote garbage in there for those subsets, and they might impact the number that's returned, although that number won't pass the check at the end, right? However, you may, now here's the thing that's tricky. You might always get garbage and miss one of the duplicate values that you're looking for, one of the ones that you're looking for. That's what I want to prove. I want to prove that you're always going to get all of those values that you're looking for, which may or may not be true, because there might be garbage in there. Like the filter might not always be strong enough. That's what, I don't really have an obvious proof in mind that the filter's not always strong enough, or an obvious proof in mind that the filter's always strong enough. All I need is one counter example. If I hit the submit button, I'll probably hit the test case, and that'll be that. And that'll be very sad, because I won't know what the algorithm is to solve it. I think, also it's midnight, it's time for bed. It's time for bed. Let me think here. Well, let's up here more than the floor event over 3 times. All elements that appear more than the floor. What would be a case, a test case, an example? I have to think of an example where it might fail. You would have to have garbage for every filter So you have like let's say you have just a lot of bits in a particular test case, and it's a passing test case. The problem you would have is you would have to have every bit, there'd have to be some other number that, for every bit, there's some other number that has, I guess, most of the bits that you're looking, no, it would have to be, it'd have to be some other number, so it has to be for every possible returned value. So that means that for the winning ticket, there's every single bit that you go through, you would get that bit, but there'd have to be an extra bit that you get every time. And if you get that bit every single time, that means no matter which bit you filter on, that means that other number, or there has to be enough of the other numbers that share bits such that this extra garbage bit will be present. Now, by the nature of this garbage bit, it's not present in this n over 3, right? So it's about a third of the numbers. This bit's not present in this third of the numbers. I mean, maybe we could suppose that it's present in, let's just say there's one bit that's present in all of the other possibilities. So let's see if we could try to break this. Let's see if we can come up with an example, right? So let's say 1, 0, 1, right? And we want to do 9 numbers. It doesn't really matter. Let's put this 9 times. 1, 1, 2, 3. 4, 5, 6. 7, 8, 9. Okay. So my thinking here is we want to somehow break this. So we'll have these 4 up here, and we want to somehow get garbage into this algorithm. Now we pick this bit, we would get all of this, and then maybe get some other garbage here. We'll pick a bit that's just always there. Now all of these bits have to be present in these other numbers that we're interested in, because we need this bit to show up in at least 4. In at least 4 cases, this bit shows up where these are still all different numbers. I think this works if you do it this way. You can add some zeros to make it work. I mean, to break this algorithm. I think this is a test case that breaks things. So you can just add zeros, and we'll just say we want 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay. And then these could all just be zeros. 1, 2, 3, 4, 5. Trying to, okay. Okay. I was going to, as I was saying, I was going to, try to make this like somewhat clean, you know, somewhat, I guess, straight or what have you, but not straight, but I don't know, somewhat clean, but that was not, it wasn't working out. Making that straight, I guess, or not straight, like somewhat nicely formatted. You know, it's kind of the gaps between them are kind of not very uniform. It's like not very well drawn, but that's okay. So we have 9 numbers here. Now the algorithm we've got, it's gonna return all these 1 bits. Every time it processes one of these 1 bits, it's gonna return that set of bits. However, it's also going to return these 1s because all 9 numbers fit in that set for every one of these 1s. And every time you're also going to get these 1s, 1, 2, 3, 4, 5, these 1s, which is enough to reach the target. So so you'll never get just this number alone. Because every time you filter, you're going to get, when you try to filter out all these other numbers, you'll filter out these numbers, sure. However, you won't filter out this one. So this is actually a failing test case. So this is, what are these numbers? Oh gosh. I could probably print them if I wanted to, I guess. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 12. 12. Let's see. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And there's this one, oops. This one, this one, this one, this one, and this one. Okay, what do we get? Um, 1, 2, 3, 4, 5, 6. Okay. Just comment these out for the time being. Now, if you make this as a test case. Okay, well, it's fine, I guess. This is 1, 2, 3, 4. This should be a failing test case. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, that should fail. What? Are you kidding me? Is this a joke? What? What do you mean? No, that's wrong. That's so wrong. What are you talking about? What? 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 Oh, I know why. I know it's missing. Ah, no, no, I messed up. That one's fine. This test case. This is the one this is supposed to have a 1 in all of them. I forgot. It does, no, we do have a failing test case. Yeah, we're fine. We're okay. Okay. One, two, three, four. Now this should fail. There we go. Okay. Expected 2720, output nothing. That's not really correct. Yeah, right. Because now this number that we get over here, all these numbers, it doesn't match anything, right? Because we're gonna get this thing with an extra 1 in there, and it just doesn't match anything. So, huh? Yeah. Could alternatively, no, what's interesting though is if instead of matching to see if we're equal with all of these, match to see if when you take the AND with everything, I want to say you can, no, man, I thought I was so clever. I thought I was so smart figuring this out. I think I have to come back to this later. There's probably something like a lot simpler that you can do to figure this out. If you use this number that you get, whatever this is, and you AND it with this guy, that's actually the right number. Interesting. Excuse me, interesting. Shucks. Yeah, this filter that I've described here actually isn't strong enough. It's not strong enough. That's actually the problem. The main problem is we need a strong filter that'll get us some constant number of values that we can then check for duplicates on. That's the approach that I'm trying to take here. Excuse me. I'm glad that I was able to figure out the breaking point though. Like this in theory where you can break it, and then I was able to generate the test case. That's pretty good. But I really wanted a bed, man. What's the solution then though? How do I floor event over 3 times? Tempted to just look at the discussion and give up. So tempted to just give up. It's too much time, you know. I can lay down. I think I'll just fall asleep if I lay down, though, you know. How to do, how to do. Okay, I have an idea. How about this? For each bit, you filter on each bit all the numbers that have that bit, and you want to figure out which of those numbers are equal to each other. How do you do that? Maybe you could do a set partition or maybe do a radix sort. Ooh, I didn't think to do that. It's probably, oh gosh, that's how you do this. Duh. Oh man, you gotta be kidding me. Yeah, so, okay. you just perform a radix sort. That's all. And then oh, this is so much easier than I thought. Oh, I feel so dumb now. Yeah, radix sort is fine. Okay. So the way a radix sort works is no kidding. Oh, excuse me. Wow. Wow. I can't believe I did that. I feel like a real dummy right now. Wow. So the way radix sort works is excuse me, it's basically a digit by digit kind of evaluation. And what you do is you say, like, take all the digits that start with a 1, and you're going to put them, let's say, behind in the all the digits that start with all the things that start with a 0, put them in the front, right? Move them all to the front, and then all things that have a 1, those come next, and then you repeat one, on sort of the next digit, all the things that have a 0 are going to go to the top half, and all the things that have a 1 are going to go in the bottom half again. Yeah. And it's all relative to their whatever position they're in currently. Just thinking, how do I do this properly? Oh, switchy. Oh, that feels good. It's gonna bleed if I keep scratching like that. Huh. Just thinking, how do I? You can actually use your the sorting algorithm of your choice to perform the radix sort. So we can use the what you might call the Dutch flag algorithm or what have you. Or really, it's just if it's a 0 or 1, there's a starting point and ending point. And so we might want to just write our own little sorting algorithm here. Sorting routine. Make it a stable sort. And then that would then we can use the routine I was describing before, where we can check the frequency. Just thinking, how do I? I want to say I'll just have a pointer, and you just swap. So you have a pointer pointing to the initial position, and if it's a 0, if you see or pointer pointing to a spot, so you're going to go loop through each number. You say, okay, if it's a 0, then don't worry about it. If it's a 1, then we want to move, I guess, all the zeros to the left of that 1. So we'll leave 1. Then we see a 0, we'll swap the 0 with the 1. And then we go to the next, we see a 0, swap it with the 1. See a 0, swap with a 1. And keep moving. And that pointer is going to point to, I guess, the beginning of the 1s, or just after the end of the 0s, we'll say. Yeah. So we'll call it first 1. And so we'll swap. All right, so we'll do one routine to swap everything, so all the 0s and the 1s are in the right spot, and then we'll repeat that in a radix over all of the indices. So we'll do, I don't know, call it swap sort, or a simple sort. So index, we'll have an index, and we'll say also numbers here, nums index, sure. And now we're gonna say int, I guess we'll we'll call it, b equals 0. Say for it really should be, I guess b is less than nums.size, increment b, and we'll say bool check is equal to 1 index and int val equals nums of I guess it would be b, and val is, when you AND this, it's either 0 or 1, right? Yeah, turn that into a Boolean, right? And do that conversion. And now we say, okay, if check, then we're going to want to, so initially if check is true, then we can swap nums of A and nums of B and increment A, right? Right, if they're both ones, if it's a 1, we could swap them, not a big deal. If it's not a 1, it's a 0. No, I would say if it's not a 1, if it's a 0 you can swap, that's fine. And you're going to increment both of them. If it's a 1 though, you're not going to touch 1s. So if the initial one is a 1, you're going to leave A where it is. Excuse me, you're going to leave B, we have A where it is, and B is going to move to the right. And then now, if B is a 0, then you're going to swap. Let me do this check, let's say is 0. Is 0. So if it's a 1, it means it's a 1, and then negate, so is 0. So if is 0, that's when I want to perform a swap. And A will always be at the 1 position, or a 0 position that we don't care about. Yeah, I think that's all I have to do. And so that'll swap the numbers. It'll be a stable sort. So you won't mess up your previous, as you move bit by bit, you won't mess up your previous sort. And so now you say for I equals 0, I is less than 32, plus I, int which bit is going to be I. You actually want to go the other way around. You want to go left to right, from back to front. And you're going to say simple sort on I. Right? And then you're going to do a check. Now you can count the frequencies. So after sorting using stable radix sort. Count. Count the frequency of each number and turn. Okay. With the appropriate frequency, so we want to say 4. Okay. So loop through each number, and you have an iterator to the previous, an iterator to some current value, and say if they're equal, increment the count. Right, obviously previous is going to be equal to the iterator is pointing to here. Previous is going to update to this iterator. And so they're initially equal. Excuse me, this iterator moves forward. They're not equal anymore. Then you say, okay, if the count's greater than or equal to the target, which it shouldn't be, then push back previous value and re-update the count to 0 and set the previous value to what the iterator is pointing to now. And now point the iterator to the next thing and say if the iterator is equal to the previous. I think we should actually do I wanted to say something like the count should actually start off at 1 because the previous is already at least a value of 1, and this should really start off at begin plus 1. So count is 1 if current value is equal to previous, increment the count, otherwise perform an update, and kind of keep repeating this over and over. And I think we'll just say if we just have to do this one more time over here. So if count 1 additional pass afterwards. So if count is greater than or equal to target, then push back previous. So if they're equal to each other, you're going to increment the count, and previous will update to the last iterator, and then this is going to go off the edge, and so the count won't get potentially counted. If they're not equal, then this should have a count of 1. So if they're equal to count. If they're not a count, then the previous sort of range, I guess, will be checked here, and then previous will be set to where the iterator is pointing, the iterator will go off the edge. The count should get set back to 1 actually every time. Yeah. And let's see how we do. Compile error. Oh. Never mind. Never mind. Got it right. Okay. All those test cases now. There you go. That's a lot better. That's a lot better. All right. I think this is always correct. This is this took me a really long time, but if I realized this sooner, that would have been good. You can technically use this radix sort for any vector of integers that's it's technically constant time linear time sorting. If you have all of your integers are in like a small, what do they call that? Like a finite number of bits, we'll say. This is kind of a hack though, I guess, because, you know, we're assuming our integers fit in a small size, I guess. Alright, let's go for it. Oh. Ooh. I thought there might be a test case that I failed, but I kind of didn't want to take the time. Patience is wearing thin already by now, which I guess is kind of my own fault. It's not, you know, no one's fault but my own. Output expected. Why don't we get 3? Oh. That's not sorted. Well, that's not sorted. What happened? What happened? Why didn't that sort properly? That should sort correctly. I don't know, man. Oh, that didn't do anything to these, huh? They stayed exactly as they were. And no sorting was done. Huh. That's not good. That explains some things. These test cases, I think, were all sorted. Okay. Okay. No kidding. Gee. Gee. Huh. What? Oh, there's some sorting towards the bottom here. That's not correct, though. That's definitely not correct. Can we print as Boolean? No, I want to print. The bits of a. No. Oh no. That's the right routine to get the bits. That's so annoying. There's a way to... No. I want to write a routine just to print the bits. It's so annoying. Ah. Huh. Excuse me. So this is zeros all the way down to 1, then a 0, 1, 0, 1, then zeros all the way down to 1, 0, 0. And this 4 should come before the 5. This is not correct. This is not correct. Alright. Bits. I think that's all you need. What does that look like? Ooh, excuse me. Why are these just a bunch of 1s now? Oh. Hey, that's got something to do with it. Oh. Yeah, okay. Gee. Okay. That's a little bit better. 4, 2, 4. Oh. Got it. Forgot. Okay. Yeah, so it's not the most helpful. But you could do it this way. Excuse me. One, 3, 3, 2. Oh, this space must be okay. Excuse me. So the first 30 passes. Let's see. It's 32 passes, right? So 31, 30, 29, 28. First 28 passes, we don't care. Or 31 minus 28. All right. Excuse me. What we're gonna do? Gonna do it this way. One, 3, 3. So this pass here should take all these zeros and push them to the top, and all these ones push them to the bottom. Which is not what happened. That means 4 should get pushed down below all the 3s. Yeah, these 3 should come up, basically. And 4 should be right. So the 3s did not come up. So what happened here? Why did this not sort properly? That just didn't sort properly, man. Is 0. B is 0. The value there is a 0. Right, this top one is 0. Excuse me. Oh, that's probably why. This has got to be not equal to 0, right? So there's a Boolean value now, true or false. And you can say 0 equals 0. That might have something to do with this. No, it doesn't matter. 3s never get moved to the right spot. At one of these points, all the 1s should be down here. All the leftmost 1s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, How does that work? How does that? Okay, get this value. Take a look at the index. It's a 0 or a 1. Alright, that tells you that value if it's a 0 or 1, correct? So if it's a 0, then what you want to do is swap nums of A with nums of B. Let me just see, hold on a second here. Okay, let's see this now. Index of 0 on test. That's 1 AM over here. It works. What do you mean it works? How does that work now? What are you talking about? What in the Sam hell is going on here? This is not what I was expecting. So I'm throwing in 1s and 0s all over the place. Uh-huh. No, that doesn't work properly. um, What is going on, man? Why doesn't this work? I don't get it. My head hurts. This is not... Does this make any sense? Does this make any sense? Oh. Okay, so that kind of helps a bit. That is, it's not sorted the way you'd expect. Oh. Right, so the sort is just not working properly. Why though? I don't get it. I don't get it. Oh, I'm so tired. Something is wrong with my simple sort. Something wrong. Something wrong. Who knows? Who knows? It's just wrong. I don't know what to do. I don't know what to say. It's just wrong. Somehow. It's gotta be this routine, right? Because erratic sort works. It's correct. So something's up with this routine. It's gotta be. Sort with zeros on the left and everything else on the right. It worked. It worked when that was the only set of numbers that we were looking at. When you simple sort a few times, though, it gets a little funky. So A should be pointing to a 1, and B points to the next number. And so if B is a 0, then you're going to swap A and B, and then increment A. So A should be pointing to a 1 now, possibly. A should always be pointing to a 1, or a 0, but more likely than not. A 1 before the yeah, possibly a 0 or a 1. The first one on the right side. What the heck, man? This is ridiculous. Why is it not sorting properly? Why? Why? Alright. So we got 1, 2, 6, 5, 3, 5, 7, 1, 0, 0, 0, 1, 1, 1. Okay. That doesn't make a lot of sense. Oh no, it starts off like that. So 7 and 5 should be... Seven and 5 should be moved to the left side here. This first run. Or yeah, the second routine should have 7 and 5 all the way on the left. Oh no, 1s are on the right side, so 7s and 5s are all to the right. Which seems to be correct, yeah. Anything above 4 is to the right. Which is good, it's there. And then next thing is anything... Oh, maybe I am doing this wrong. Now I'm thinking about it. Maybe I'm supposed to sort from right to left rather than left to right. Yes, I think that's my problem actually. I think I did it wrong. Oops. Yeah, okay. I mean, I think it would just sort backwards. No, it's not sorting correctly. And no, you do need to sort. I'm so confused. I am so confused. No. You have to be careful with radic sort. It's gotta be. You have to do the most significant bits last. Yeah, I made a mistake, right. Or is it the least significance last? Right, because if you move the least significant, yeah, you can end up moving, right, so if you move the most significant things, it doesn't matter, you'll overwrite the least significant values. What the heck am I doing wrong here? I'm doing something really funky here. What? What did I do, man? I see that 7 5 5 5 7 5 6 5 7 at the end there. I think what you're supposed to do is you don't radic sort on the entire next wave, I think you're supposed to radix sort within each split block. Oh, yeah, that's I implemented the radix sorting correctly. That's why. Duh. I'm really tired. I blame. Well, take no responsibility. No, I just did it wrong. That's all. It's just wrong. It's wrong. It's wrong. It's wrong. Yeah, we can do this recursively. That's fine. So the way this would work is I have this simple sort, and then okay, we'll just do simple radix sort. All right. Now this index, and we say, okay, we have this A and B now. B goes off the edge, and A is pointing to. A should be pointing to the first point where 1 starts, 1 begins. We can just do A and B and leave those out. And we'll just say int C. Could be iterators, I guess. Less than, say B. Yeah. Okay, and then we're going to want to call we'll say, yeah, we'll go all the way down. So we'll say if index is greater than 0, then we're going to simple radix sort from A to C. Or from, yeah, A to C, from C to B, with index -1. Nums F. And this is actually so the range should change slightly. We say here, we don't want to we don't recurse twice if I guess if A equals C and this equals B or something like that. What does this look like now? The thing that's awkward about this is we don't know what the values are. We probably want, shucks. Because A could be pointing to a 0, you know. If it's zeros all the way across, if there's at least one 1 in there, then I think A points to a 1, or C is going to point to a 1. I think I did this wrong. I think we want we don't want C. Yeah, we want temp to no, A to temp, that's what it is. Temp to A, really. And then from A to, I guess it would be B, yeah. So A to B inclusive, and then temp to A inclusive. And now the question is A a 0 or 1? If A is a 0, then we want to include A in the first shot and do A plus 1 down here. But if A is a 1, then we want to do A minus 1 and A over here. So we say A is going to be equal to nums of A. Really, it's temp is the one. Oh no, A, yeah, nums of A is if it's a 0, then we want to decrement A. We want A to be left alone. Otherwise, if A is a 1, we want to actually decrement A. Confusing as that might be. That's the breakpoint between the zeros and the ones on the left and the right. And then you want to recurse them inclusively. Eventually you might hit a point where A is equal to B, and in that case, so temp equal to A, or these could be degenerate too, that's another thing. Temp is equal to A, C is equal to A, C is less than or equal to B. So you execute this because C is A and A is equal to B. And you say value nums is boolean 0, it's not 0. If it's 0, you swap with itself and increment A, and then increment B, or increment C rather. So now A is past B, and C is past B as well. And then you do this routine. So you can just perform a simple check and just say if if I think otherwise you just return. Can A be off the side of the map? I don't think so. Off the side of the. I don't think it ever goes off. It's just. I think you're okay with this. I don't know. This is such a funky implementation of a radix sort. It's like a really wonky implementation. You could do it this way too. I've actually never written a radix sort before, I think, so this is interesting for me. Just don't do anything if your lines are crossed. I don't know what this is gonna look like. A and B, 0, B will be nums dot size -1, nums, simple radix sort. Okay. Wow, this problem, I've been at this for a while, huh? I have work tomorrow too, man. Oh, that worked. Okay. Alright, looks like I've corrected my radix sort now. Great. Runtime error, nice. Okay. That's pretty funny. I don't know how simple this radix sort is, man. Alright, now let's play the game. Which one of these is the problem case? It's definitely got something to do with that A thing going on where there's some edge case here. That's fine. That's one of these. Bet just one of these cases. Nice. Is it just this one? Oh, okay. Well. I guess the radix sort doesn't work on just one element. Oh, okay. Some more error cases here. Alright, what happens if you have two elements? I think it's this that causes the error. Yeah, I'm pretty sure. Yeah. So, why though? I think because A can go off the bounds. Yeah, if you swap the two values, and it goes out of bounds here. In that case, we actually don't really care. I think this is the only case where nums of A, where it's actually 0 is when you go all the way to the right. Right, because if there's a 1 anywhere, then A is going to be pointing to that 1. Yeah. I don't think you even need this. I think you just say if. Yeah, I think you just leave it. What? What is going on here? Oh. What? Why? What? Question is, where exactly do we get a runtime error? What is causing the error? That's the question. I don't even know. Alright, we don't make it to temp A nums F A is greater than B, greater than equal to num size, is less than 0, temps equals A, you got array access here, so C is A, but, oh, I guess that's the other one. Oh yeah, that's my mistake. I didn't really think about that. Yeah, okay. I don't know, I kind of, I don't think sometimes. That's actually really obvious. That was really pretty easy to take care of, pretty obvious. I also don't need that either. The wrong answer now. What? That's the last one, huh? That one's wrong now. What happened? No. It's freaking 1 a.m. where I'm at, man. I need to go to bed. Oh. Oh no, it stopped working now. What happened? No. Come on, man. Why? It was working before. What happened? What happened? Are you serious? Are you serious? What? Are you serious? Oh. Yeah, you need that little piece of code there that fixes where A ends up, I think. No, A is always, I think A is always here, like this. Are you serious? How is this real? Okay, I think we got there. Just kind of goofed. Oh. Gosh, man. I think this also works on these other cases now, by the way. Let's see. Yeah. This probably also works here too. Yeah. Okay. Okay. just simple recursive erratic sort on the binary, on the bits. And this is all constant time. Not constant time, it's all, this is linear with constant memory, because all of these calls are what do you call that? It's 32 log 32 number of calls, and the total amount of work is 32 times n, which is interesting. And then it's O of n. Alright, I think we got it. Let's see how we did. Did it. There we go. That was so much effort to do this with constant extra memory. That was really involved. Yeah, that was difficult. Oh, I need to sleep now. Oh, so much effort. Gosh. Alright. I'm gonna get going. Thank you for watching. I appreciate it. Talk to y'all soon. Oh, my shoulder. Oh. Yeah. So basically, TLDR, I just used radix sort to sort it, and radix sort, if you're only working on the bits, it's efficient. So, not just efficient, but it's doesn't use extra memory, and it's linear. Yeah. All right, I'm gonna go. Again, talk to you soon. Thanks for watching. Have a good. If you like this stuff, don't forget to like and subscribe. Take care.